This will be the first lesson that will be video broadcasted on balanced and unbalanced forces. So we had worked in class with the Funyun activity where we tested and designed techniques of showing balanced and unbalanced forces. Now what we want to do is actually show how those look graphically using physics diagrams. And the physics diagrams we use are called force diagrams or free body diagrams. And they can essentially be constructed by simply asking 4 questions. The first question that you want to ask is there gravity? And gravity, you know, is anything that on Earth experiences gravity. The only place that doesn't experience that is space. So we're going to write the letter F for force, and we're going to write a small subscript of G to let you know that that force we're looking at is gravity. So G stands for gravity. And we know that gravity is pushing down or pulling us down, and so for that reason a force, gravity force, is always shown as an arrow pointing down. Next question is it sitting on a surface? An object that's sitting on a surface is actually being pushed up by that surface, and we call that normal. So this pushing up of the surface onto the object is considered a normal force. For that reason, we say Fn. Again, N stands for normal, and in that case, it's an arrow pushing up. Next question, is something pushing or pulling it? And this is usually because you're applying a force. For that reason, it is called applied force. And we call this Fa. So Fa could either be in this direction, where you're maybe pushing or pulling something to the right, or it could be an arrow pointing this direction, where you're either pushing or pulling something to the left. The last question I want you to ask is there friction? And friction essentially is a force that goes against the applied force to either slow things down or speed things up. So, if you have an applied force with an arrow moving this direction, and there is friction, then you would have to have a force going opposite that. That is your friction force. So F stands for friction. Okay? If you have an applied force that moves in this direction, and it's on friction because it's on a surface, then the friction force is opposite that. So those are essentially the arrows and what they are, what they stand for. So let's actually use this as an example, okay? But before we do that, let's talk a little bit about what a vector is. So I've been drawing arrows, and essentially what I've been doing is I've been drawing a vector. A vector is simply an arrow, but it's a unique arrow because, one, it shows direction of force. And secondly, it also shows how much force. So for example, I'm going to draw a vector right here, in other words, an arrow. And this tells me that the force is either pushing or pulling to the right. Okay? I might draw this sort of arrow. And this tells me it is pushing or pulling to the left. I also might draw an arrow pointing up. In this case, it's pushing or pulling up. I think you get the general gist of it. All right, so that shows the direction of the force, but it can also show how much force. For example, I might have two arrows, and you know what? Let me actually put a different color for this one here. Let's make this one. So I might have two arrows. These clearly are pushing or pulling to the right, but there's a difference between arrow A and B, and you notice that the arrows are different lengths. The longer the arrow, it shows the more force. So there is more force of push or pull on A, and that's why we have a longer line. This one, B, has less force than A, and that's why I draw a shorter line. So, how can we put all these things together? Let's do an example, and I'd like you to draw this example as well. So let's say, for example, I have a box sitting on a table, or even better, well, we'll have a box sitting on the floor, and I'm going to have someone pull this box this direction. So box is pulled to the right. Okay, so let's draw a diagram. In other words, a force body diagram or a free body diagram. And we're going to base it as a reference point on the box. And let's look at it as a centerpiece. So we're going to place a dot in the center. And my first question, if we go back, is there gravity? And the answer is, because I'm doing this in the classroom, there is gravity. So I need to create an arrow pointing down and label it FG. All right, so there is force of gravity pushing down that box onto the floor. The next question I need to ask is it sitting on a surface? And the answer is yes, it is, because it's sitting on a floor. So for that reason, I know I have a normal force. And because it's sitting on the floor and not sinking in, I may need to make certain that my arrow is just as long as my FG arrow, because they are balanced forces. The box is not moving down or moving up. It's staying in the same spot. And just as the Funyun lab, when the forces were balanced for an object at rest, they actually stayed in the same spot. All right, so that is and my apologies, this should be FN. Good. All right, next is this box is being pulled. So I am applying a force. Because it's being pulled to the right, I actually need to draw a force vector, or a vector, pointing to the right, and I call this FA. Now, because it's not on a super smooth surface, this floor has some bumps into it, it's kind of experiencing friction, not a whole lot, and so for that reason, I'm going to draw a force diagram pointing to the left, and this is my friction. Okay? So, this is how they all combine together. You notice that my friction diagram arrow vector, I should say, is a little bit shorter than all the others. And because of this, we call this unbalanced force. So for your Funyun lab, I asked you to do balance forces, in which case your vector for the balance force with maybe 2 people should be equal and opposite. That is balanced. For a vector or free body diagram that experiences balance forces with 4 people, you would have something that looks like this. All the lines are equal, they're opposite each other. Another example of balanced forces. Now, if I drew a free body diagram that looked like this, it is considered unbalanced. And if I drew a free body diagram that looked like this, it's also unbalanced. So, why are these unbalanced forces? Well, this one, first of all, has too short of an arrow. It's not equal and opposite to the opposite arrow, so it's unbalanced. For this one, same scenario. In some cases, you might see the forces to be like this. These are also unbalanced because they're not equal and opposite. So let's do one last example before we end. See if I find an empty slide. Nope. What we'll do is we'll go ahead and erase this slide. So let's say, for example, you have an object hanging, a ball hanging from the door frame, and my reference point is the ball. Okay, and it's simply just hanging. Draw a free body diagram of that. Just pause it, and then I'll give you the answer. So pause now. All right. So hopefully, for your free body diagram, you went through your questions, and the first question you asked is there gravity? Well, it's hanging from the doorway, so you know that it is experiencing gravity. So you write FG. Is it also feeling any sort of normal force? Meaning, is something pulling or pushing it up? The answer is yes. Actually, that string is kind of pulling it up so that it doesn't fall to the ground. And because it's at a complete standstill, we say that it has a normal force. Is there any force being applied to the left or to the right? And the answer is no, there isn't a force. And so for this reason, this free body diagram only contains 2 vectors. But is it considered balanced or unbalanced? The answer is it is balanced. And that ends our introduction on balanced and unbalanced forces and how you would draw them using free body diagrams or force diagrams.